All right, so when you take the derivative of a logarithm, we're going to do it in the special case first. And the special case is the derivative of ln of x. The derivative of ln of x is 1 over x. Now, one of the things that makes this derivative interesting is that the answer is x. It's basically x to the negative first. Okay, and if you think about how we get derivatives, we always use 1 power below what we started with, right? Okay, if you have a quadratic function, x squared, that derivative is x to the first. If you had x to the 5th power, then that derivative would be an x to the 3rd power, right? So you're always lowering 1, okay? So the question is, what would you have taken the derivative of in order to get x to the negative 1? Well, going 1 power back up, it should have been x to the 0. But x to the 0 is a constant, right? X to the 0 is 1, and the derivative of all constants is 0. So up until now, we didn't really have a way of getting a derivative that resulted in x to the negative 1 power. The log function fills in that gap. Okay? So the derivative of ln of x is 1 over x. Find y prime if y is equal to the natural log of x plus x cubed. So y prime is equal to the derivative of the natural log function, which is 1 over x, plus the derivative of x cubed, which is 3x squared. All right, example 2. Find y prime if y is equal to the natural log of 7x. So this one is going to involve the chain rule, because you're taking the derivative of not just the natural log of x, but it's the natural log of some other function, right? So we start in the same format. The derivative of the natural log function is 1 over, and then it's whatever you're taking the whatever the argument is for the natural log. So it's 1 over 7x times the derivative of the inside, which is 7. And then what happens with the 7s? They cancel. And it is actually 1 over x. So it's actually the same as the derivative of the regular log. Now there is an algebraic argument that you could use to show that this should work out the same way. Let me briefly talk about that. The natural log of 7x is really the natural log of 7 times x. And you know that if you have multiplication inside a log, you can split that up with addition. Okay. So then if I take the derivative, then the derivative here, well, the derivative of the natural log of x is 1 over x, and the natural log of 7 is just a number. It's, whatever number that is. It's probably around 2 something, right? And the derivative of a number is just 0. So this is 0 plus that, which is just 1 over x. Okay. So it makes sense to have this be the same thing. All right, in example 3, we have y is equal to x times the natural log of x. So the derivative, we're going to use the product rule. It's the derivative of the first one times the second one unchanged, plus the derivative of the second one. So here the derivative of the natural log function is 1 over x times x. And then we can simplify a little bit. We have 1 over x times x, so that's 1. So this is the natural log of x plus 1. And that's it. In example 4, we have y is equal to the quantity natural log of 3x squared plus 1, all of that squared. In order to do this derivative, we're going to need to use the chain rule. And in fact, we're going to have to use it a couple of times. So to do this derivative, we first need to know what the outermost function is. what's the last thing you would do? You would square it. So the first derivative we take is the derivative of the square function, which would be 2 times the inside and I'm going to write that as 2 times the natural log of 3x squared plus 1, and then, for emphasis, raise that to the first power. Now we need to take the derivative of the inside. The inside here is the natural log of 3x squared plus 1, and so this is the derivative of the natural log function. So it's going to be 1 over everything that's on the inside. Okay. But the inside here was not just x either, so we have to isolate what that inside was, and that inside was 3x squared plus 1, and we have to multiply by that derivative as well, and that derivative is 6x. Okay. This is why it's called the chain rule. You keep chaining on links that are the derivatives as you work your way inside to the middle of the function. Okay. Does everyone see how I've implemented the chain rule twice in this problem? Okay. First time was we had a square function, we got to the inside, took the derivative of that inside. That inside function was another composition itself, so we take that derivative on the inside as well. Okay. Now we can do a little simplification here, not much. Let's see, I can do 2 times 6x, and that's 12x, times the natural log of 3x squared plus 1. No need to write the 1 power. We'll just leave that off. And then 3x squared plus 1. Now, is it possible to cancel off these 3x squareds plus 1? It's not possible, right? Remember that this 3x squared plus 1 on the top is actually the input or the argument for the natural log function. You can't cancel off the argument of the natural log function, right? You can't just have natural log sort of sitting out there by itself. It's got to be for the whole thing. All right, so just like we modeled the e to the x and then we did regular arbitrary bases, a to the x, we do the same thing with the logarithm. We started with the natural log function, and that derivative was 1 over x. Now, how do you get the derivative of a log function that's in any base? Well, it's still 1 over x, but then we have this extra factor here, this natural log of a, and that is in the denominator. Okay? So the a again here is the base. So suppose you want the derivative of log base 3 of x. Well, the base is 3, so the derivative would be y prime is equal to 1 over x times the natural log of 3. There's a certain amount of symmetry here that existed between the exponential function and the log function. When we took the derivative of an arbitrary base raised to a power with the exponential, we multiplied by the natural log of the base. And then when you do it with the log, you divide by the natural log of the base. So you have that sort of duality going there. In example 6, we have y is equal to log base 12 of 3x minus 1. So to find the derivative, this would be 1 over the argument of the logarithm, and I need to put this in parentheses, so it's 3x minus 1, times the natural log of the base, so this is the natural log of 12, and then I think back to what the argument was. Was it just x? No. So I have to chain on that derivative, and the derivative of the inside is going to be 3 itself. And then you can multiply that out here. So it's 3 over 3x minus 1 times the natural log of 12. Nothing cancels there. So that's just it.
Why do you never do chain on this one?
You always think about doing the chain rule. Okay? And what you're observing is what is the inside function. The inside function here was 3x minus 1, which has the derivative of 3.
Okay.
Yeah.
So that has to
So,
do with that too.
yes.
Okay.
And sort of more generally, suppose that the inside had been x. What's the derivative of x? 1. So you're always multiplying by 1 anyway, so you're sort of always doing the chain rule, you're just not always writing the chain rule. Yeah. All right. In example 7, y is equal to x squared times log x. Who wants to volunteer this one? Anyone? Anyone over here? Essay, what'd you get?
I got 2x log x plus x squared over x ln 10.
X squared times, let's see, 1 over, what'd you say? X?
X ln 10.
Okay, very good. Yeah. So the key to this one is to remember that this log is called the common log. And the base of the common log has base 10. Now, we can reduce this a little bit. We have 2x log x plus, and then the x squared and the x here cancel. So this is x over natural log of 10. All right, questions over that one? Yeah.
Where I stopped was I had 2x log x plus x squared over x ln 10, and so do like the x's on the outside of like the denominator right there. If you have like x like cubed and then it's like x ln 10, could you like simplify it to be x squared and then always cancel out?
Yeah, like this x squared here can be simplified to be on top of this fraction.
And that's where I had it. I just didn't know if it canceled out.
It will. Yeah, it will cancel. Yeah. Yeah. Yeah, the only thing you got to be careful of is how many things do you see in this denominator down here? 2 things. Yeah, you have an x and you have an ln of 10. So you can't cancel things inside the ln with things that are on the outside.
So you couldn't cancel like a constant, but you could cancel.
Right. Right. Yeah. Okay. All right. Let's look at example 8. Water is being pumped into a reservoir. The amount of water in gallons in the reservoir T hours after the pump began pumping is given by W of T is equal to 200 minus 100 over the natural log of T plus 1. The first question is, how much water is in the reservoir when the pump began pumping? Now, I made a mistake. This is my fault. I wrote this question, and that problem doesn't actually work. Not with the given equation. Because if T, when we go to when the pump began pumping, that would be T is equal to 0, right? What's the natural log of 0 plus 1? It's the natural log of 1, which is 0, and that's what I have in the denominator. So I can't do that. So, I'm sorry. So we cannot do that one. We could do it like, what's the amount of water in the tank after an hour? Anything other than T equals 0 would work. But that one doesn't work that way. So we skip that one. Okay. Come on. Oh, there it goes. Autosave. All right. All right. Question B, though. Find the rate of change in the volume of water in the reservoir after 2 hours and interpret. So if we have the W function, which is 200 minus 100 over the natural log of T plus 1, if we want the rate of change, what function do we need? We need the derivative, right? Rate of change implies derivative. So let's find W prime of T. The first part of W is 200. The derivative of 200 is 0, so that's gone. Then I'm going to pick up this negative right there. Then I want to do the derivative of 100 over the natural log of t plus 1. I'm going to do this one using the quotient rule. Okay? So the derivative of 100 is 0 times the bottom unchanged minus the derivative of the bottom, which is 1 over t plus 1, and then I need to tack on the chain rule, the derivative of the inside of the log. So the derivative of t plus 1 is just 1, times the numerator unchanged, 100. All of that divided by the bottom squared. And then I would simplify this a little bit. First thing is this term is completely gone because that was 0 times all of that. Next is this negative, and because I only have one more term in the numerator, those two negatives combine to become a positive. Okay. And we end up with 100 over t plus 1, all divided by the natural log of t plus 1 squared. Now notice that I have a little fraction inside of my bigger fraction. So I'm going to use the following technique. I'm going to multiply the big fraction by the little fraction's denominator over itself. So this is going to be t plus 1 over t plus 1. Okay. When the t plus 1 is multiplied by this numerator's fraction, the t plus 1 part cancels, and that is going to leave me with just 100 in the top. And then the bottom one is just, there's nothing to simplify, it's just there for the ride. Like so. So that is how you simplify the derivative. Now the question asked for the rate in change in volume after 2 hours. So we need to take this function and apply time equal to 2. So that would be 100 divided by 2 plus 1 times the natural log of 2 plus 1 squared. And I have worked this out for us ahead of time. And this is 27.618 gallons per hour. And Gary?
Just a quick question. On part A, is that an example where you could use a limit to determine, like, you could approximate, like, at t equals 0? A limit?
You could use a limit, and it would blow up. It would be infinite. Yeah.
Okay.
Yeah. No, you could certainly use a limit, but then it would still give you. It would actually, if you did the limit, I think it would tell us that there was an infinite amount of water in the tank. So that's no good. But yeah. Okay. To finish up part B, we need to write a statement for the interpretation. So the statement we could have is maybe something like, the amount of water in the reservoir is increasing at 27.618 gallons per hour after 2 hours. When you write these interpretation statements, usually the best plan is to use increasing or decreasing to signify the sign of the answer, positive or negative. And you always want to piggyback on the verbiage that they're using. So we're talking about the amount of water in the reservoir, so the amount of water in the reservoir, and then tell me what it's doing. Okay. The other part of this that is essential is the time frame. The rate of change in the water level in the reservoir at 2 hours, it's rising by 27.6. At 3 hours, it may be different. So you have to say what the time frame is for doing each of these things. All right. Then the last question, part C, was to determine what happens to the volume of water as the pump continues to pump over time. So this phrase, over time, that is a key word for doing the limit. So we want to do the limit as t goes to infinity of the original function w of t. Now I'm going to use a similar trick to what we did last time to solve this. Let me write up the w function again for you here. This is 200 minus 100 over the natural log of t plus 1. Okay. So the trick that we used last time was to trace out what happens to the variable t, expanding it through the function until we get to the end result. So we start off with as t goes to infinity. Okay. Now, looking at the function, the next thing that happens to the t is that you add 1 to it. So if t is going to infinity, where is t plus 1 going? That is also going to infinity. Yeah. Okay. All right. And then what's the next thing that happens to the t plus 1? The natural log. All right. So the natural log of t plus 1. Where does that go? Let me draw the graph of the natural log function for you, in case you have forgotten. This is the natural log of x. It looks like this. Okay. So now what you think of as the t plus 1 is really what x is over here. And you think of this as being the argument for the log. The argument is going to infinity. So that means we are going to infinity on the x's. What happens to the y values on the natural log function as the x's go to infinity? They continue to rise slowly, albeit, but they do continue to rise, and they go to infinity as well. All right, next step is 100 over the natural log of t plus 1. Now you're thinking of this natural log of t plus 1 as a single unit. That denominator is going to infinity. So 100 over a denominator that goes to infinity goes to what? It goes to 0, right? The denominator gets larger and larger and larger. The top is staying static. It's at 100. And eventually that's going to go to 0. And then the last little bit here, 200 minus 100 over the natural log of t plus 1. The 100 over the natural log of t plus 1 is going to 0, so 200 minus that must go to 200. Now, what is the interpretation of this result? That's the full result. It means as the pump continues to pump over time, the amount of water in the reservoir will approach 200 gallons, but then that's it.